Hi there, guys. Well, we're working towards 4K in this exercise, and 4K is about the quotient rule. So we've just done the product rule, the chain rule in the video before that, and now we're doing the quotient rule. Now, again, I'm going to put a proof on the end of this video, so I'm not going to deal with this proof at the start, but they're giving you here a proof by first principles, if you like. I'm going to give a slightly different proof, which is dependent on the proof which we've already come up with from the proof of the product rule. Okay, well, first of all then, so what is the quotient rule? Here's their little box which they're giving you here, and they're saying, well, look, if you have a quotient of two functions, in other words, if you have ux divided by vx, we're always putting it that way round, so u on the top, v on the bottom, we've got this division of functions, or in other words, a quotient of two functions, then you can see that the formula looks pretty nasty. But in fact, it says alternatively, you can write it like this. And you can say, look, v du dx minus u dv dx all over v squared. Now, that's fine. You can write it like that. But personally, I would write it as v u dash minus u v dash divided by v squared. So how do you remember this thing? So let's just snatch this thing here. Okay, so it's saying from this, in this format, it's saying, look, we've got v u dash minus u v dash divided by v squared. That's going to give us y dash, if you like, y divided by, sorry, dy dx. Okay, so I mean, I guess the way I remember this is very similar to the product rule. But I know it's got a squared on the bottom, and I know it's v squared. If you remember it's got v squared on the bottom, then it starts with v as well. So you think it's going to start with v on the top and the bottom, and then it's v u dash u v dash, a bit like the product rule, except for the difference with the product rule is we're dividing by v squared, we're starting with v on the top and the bottom, and we've got a minus in between, not a plus. Maybe that's a bit of a rubbish way of remembering it. Maybe you have a better way. Either way, this is in the formula booklet as well. Okay, so we're going to look at the questions, and we're going to look at example 23. And in fact, there's only one example in this case before we get to practice. So they're expecting you to be able to pick this up pretty quickly. So there's example 23. Let's use the quotient rule to differentiate this function here. And actually, we've done this before in example 22, so we should see that we're getting the same answer as in example 22. Okay, so here we're saying y equals u over v, so u is equal to 3x squared minus 1, and v is equal to x plus 2. Now, in an exam situation, I would probably just write out these functions really clear, come up with like a box for yourself, and then say u dash is equal to, what do we got, 6x there. We've got v dash here is equal to 1. And then I would write down the formula. So our y dash, our dy dx. Write down the quick way of doing this, v u dash minus u v dash over v squared. And of course, you want to be able to do it as quick as that. It's worth remembering this. You will be using it somewhere in your exams. Pretty much 100% chance of that happening. Yeah, it's worth remembering it because you don't really want to be flicking through the pages of the formula booklet during the exam if this is just really obvious and to mind straight away. You're going to save yourself a bit of time. Okay, so we're getting x plus 2 and u dash is 6x. Let's just put 6x on the front. 6x and x plus 2, and then minus, and we have u, which is 3x squared minus 1, and then times by v dash, which was 1, and then all divided by v squared. Okay, so we've got x plus 2 squared there. Now, you notice that this way round gives you just a much nicer format than using the product rule, because you can use the product rule here. Again, remember, this is the same as doing 3x squared minus 1, x plus 2 to the minus 1. And you can use the product rule with this as a uv instead, but you just end up getting the chain rule turning up there as well. And you'll see that you get exactly the same thing. I think that you, instead of getting x squared there, sorry, x plus 2 all squared there, you ended up cancelling one of these, just getting x plus 2 to the minus 1 going here. So that's how it looks different. Okay, so there's our answer. Maybe we can simplify this. In fact, we can take this a little bit further. I didn't do that in the first example because I had these negative powers, but now you can see that this can go a little bit further, so we could simplify this further. And potentially we could even factorize out a factor of x plus 2 and cancel it. That factorizes out of the top. I don't think it does though, because x plus 2 is not a factor of this. It's a factor on this side. Okay, so yeah, actually maybe that's a little bit of a silly thought there, because in fact, maybe that's possible. I don't know, but otherwise you'd be expecting B to be cancelling from the top and bottom. I don't know. I think it's possible. Okay, but not always going to happen. Right, let's have a look at this. We've got 6x squared plus 12x, got minus 3x squared plus 1 on the end there. And of course, you can take that a little bit further, and you can say, well, that's going to give us 3x squared plus 12x and plus 1 on the top, divided by our x plus 2 squared. Okay, that's pretty messy. I don't think that one factorizes at the top. Let's have a look at what they do in the question. And yeah, so they're writing it as we're writing it there as well. Now, let's have a look at what they did in example 22. Okay, so in example 22, they didn't take it further. So they took it further, and I didn't, in fact, when I did that example. So they actually factorized out. Here we go. Let's just check that one out. Okay, so we've got. Let's copy this. Okay, that's not what I want. Sorry. It's here, isn't it? Okay. So it's this line which was kind of important, from this line to this line. So they're saying, well, let's factorize out this thing here, the x plus 2 to the minus 2. And I didn't do that, in fact, because I was just looking for m. I was just looking for the gradient. So I didn't care about putting into a simpler version of this. I just thought I'll just chuck my value of x into here to work out my gradient. Well, they've kind of neatened things up by factorizing this out, but then realizing that when they factorize this out, they need an extra x plus 2 in here. Because, of course, when you times this by this, you'll get back to x plus 2 to the power of minus 1. The minus 2 times to the power of 1 brings us to the power of minus 1. We're using laws of indices. Okay, so that's giving you the same formula, essentially, as what we're getting through example 23. You can see that they've got the two terms the other way round in the next example, though. Okay, in the way in which we're doing it with the quotient rule. Okay, so there we go. We're done with that. That's example 23. That's sorted. We're on to 4K now. But as I said, I was going to do a proof of the quotient rule. And you should be aware of these things. And you can see the way in which they're doing it. They're saying, let's do this from first principles. And I'm not going to do it like that for the moment. What I'm going to do this one is just take a little something. And what I'm going to do is I'm going to set up y is equal to my function u over v. And they're both functions of x. Okay, y is a function of x. In fact, u and v are functions of x as well. Now, the way I'm going to do this is slightly different to the way the book does it. I'm going to call that u v to the minus 1. Okay, so now when I do dy dx, okay, that's meant to be dy dx there, not du. When I do dy dx, I can now use the product rule. And now if I use the product rule, I'm going to say u v dash. Maybe I'll leave that to the second part. I'm going to say u dash v. V in this case is v to the minus 1. And then I'm going to say v dash. Now v is this thing here, okay? So it's not really v dash I need here. I really need to set this up in terms of a product of two functions. And here, this is not a product of two functions, or at least there's a function inside a function here. Okay, so w is equal to v to the minus 1. Now I'm going to need to do, okay, so let me just take this one back for a second because it's not looking that nice. So let's just call this uw. So you can take this one back and say that this is uw dash plus wu dash. Okay, and this is our u and this is our w, and w is defined to be v to the minus 1. All of these are functions of x, by the way. Now I'm going to need w dash here. Now what's the derivative of this? Well, the derivative of this function here is going to be, and we're going to need to use the chain rule. We're going to need to say, well, that we're going to times by our original power and reduce it by 1, getting this. And then we need to times by the derivative of the function inside the function, which is the chain rule, right? So times by v dash. That's just me using the chain rule there. Okay, that's saying I don't want to set up the chain rule in terms of other functions as well. So let's just leave it like that. Okay, but chain rule is saying let's differentiate v, so do dv dx. Okay, and sorry, do dw dv, but then we're going to need to remember to times by dv dx as well. Okay, that's what we're doing. Now, when we put that back into here, we're going to get u and times by minus v to the minus 2 by v dash plus v to the minus 1 u dash. We're just putting in there, we're putting back in our u dash, and w was defined to be this. So put that in there as well. Okay, now let's tidy this thing up. We should get the same answer as quotient rule. So we're now saying, let's take out here, let's write this as without negative indices. So let's say this is u v dash minus and v squared on there, minus x, we're timesing by that. And then we've got plus u dash over v. Now, if we times the top and the bottom of this by v, we're getting v u dash over v squared, and then minus this, minus u v dash over v squared. Now we can combine those things. So starting with the v's, v squared on the bottom, u dash there, and minus u v dash there. Okay, so there we go. That's proved by using both the chain rule and the product rule, and we proved both of those things before, and so now we've proved it reliant on those two previous rules. Okay, just a little extra here. This is the proof of the quotient rule which the book gives, and it's taking it right back to the limit. So this is really a proof from first principles, if you like. This is not reliant on the product rule and the chain rule, which my previous proof was reliant on. So this is a more formal proof here, and we're saying, well, of course, f of x is defined to be u of x divided by our v of x, and what we're doing here is just substituting in x plus h and substituting in x and doing a subtraction of those two things. That's just using the normal formula for the definition of a derivative. Okay, now to get to this line, it's actually not that much working out. We can simply write this as one fraction by creating v of x plus h times by v of x as our denominator here. And of course, if you remember, if you divide a half by 3, that's going to give you a sixth. So we can put this h on the combined denominator here. So that's what's happening in this line here. You see this h and the combined denominator, and then your numerator, of course, is going to be times by v of x there, and times by v of x plus h there. Okay, so there's not a lot which has gone on there. And then in the next line, we require the same trick as we used for the product rule. So again, remember we've got this v of x and u of x plus h, and then we've got this term here as well. So we've got minus u of x, v of x plus h. So that's those two. Okay, and now they've created two extra terms so that we can do this factorization. We need to factorize out v of x and we need to factorize out u of x. So that takes a little bit of creativity there. Now the two terms that they've added in the middle are not quite the same as for the product rule. So you can see that if we want to get out u of x plus h minus u of x, we're going to need to substitute, factorize out from v of x both this and u of x. Okay, so we need this term here to combine with that. We take v of x out of that, we end up with this and this. That's this and this. Now, if we subtract that term, here it turns out we just need to add that term as well, of course, make it the same thing. And then, of course, you can see that there you can factorize out u of x. And in fact, if you factorize out minus u of x, you'll end up getting plus this and minus this. Now, that gives us the definition here when we bring in our limit, okay, which we can do, of course, because there's the property of our limits. So when we bring that in, we're going to end up getting du dx for this and dv dx for this one here as well. Okay, now you can see how they've done that. You can see how they've factorized that out. They've brought the h, the divide by h, into the row above. So they've taken it from there and put it as the denominator of previous fractions. And that's allowed, of course, again, because essentially that's like saying, again, you do a half divided by 3. That's the same as doing a 6 divided by 1. Same. Okay. If you're not sure about those rules of algebra, you can always come up with these little examples for yourself to verify it yourself. Okay. And so there we go. Now we can just bring in our limits. So bring in limits to these, bring in limits to these, bring in limits to these. And you can see that you're going to get v of x there because it's not dependent on h. And this is going to be u dash, v dash. That's, they're missing something there. They're missing u. First copy of the book, so it's probably sorted out now. So there's a u there. And on the bottom, we can see that this is going to become v of x. So you'll end up having the square of those two things as well. Okay, so that's a nice proof. It would be tough to ask that in an exam situation, and to have that, just ready, essentially. You can definitely start off pretty easily. You can definitely do some working out, but this is the creative step. And then, of course, you've got your algebra of limits. And so the steps afterwards are pretty straightforward. But this is the creative step, to add something and subtract something. Okay, guys, well, thanks for listening in. Hope that's been useful. Next exercise is obviously 4K. 4K has, by the looks of things, 5 questions on there. They've got the trident of Newton there turning up as one of the curves. Very interesting. And next time round, we're talking about higher derivatives. We're talking about second derivative, third derivative, and so on. Okay, guys, well, thanks for listening in. And good luck with the exercise, and hope to see you back next time round.